Hi, everyone. So I think this is one of our last sessions today. I want to present Matthew. For the last 70 years, Matthew has been reverse engineering, discovering new vulnerabilities, exploiting vulnerable computer system, and teaching others to do the same. He's going to talk today about emulation, driving, reversing for firmware vulnerability research. Of course, during this session, don't forget to ask question with the question and answer tab or raise your hand. And that's it. Matthew, the stage is yours. Thank you.
Thank you, Eden. Hi, my name is Matt Carpenter. As he said, I just pushed 3 polls to you. I'd like to start off a very interactive presentation style, but since we can't interact very easily, I want to ask your question, see what kind of experience we have in the audience with reversing, with programming, with computers in general, and UDS/automotive CAN firmware. CAN communications. Today we are talking about reverse engineering, discovering vulnerabilities, and specifically focused on ECU firmware and the impacts that emulation or partial emulation, as we'll talk about it, can do to help your reverse engineering. A little bit about me, as she described, a little bit more. I'm a father, husband, Christian. I've been exploiting things since 2004 and just learning and growing. I love to ride motorcycles, and I get to play on Hackasat hacking team here come October. So hacking is hard work. Reverse engineering, vulnerability research, the details, it all matters. And it takes a very special mindset. And unfortunately, with a lot of work, those minds can get tired or bored. Sometimes the grind makes it very difficult, but the beauty that we get from doing so and hopefully finding vulnerabilities and making good use of them or fixing them is a great reward, but the process can get sloggy sometimes. Within a car, we've got, so in 2016, it was estimated about 150 ECUs in the high-end luxury cars. And I have to admit, or I have to believe that the average vehicle has just continued to add in more. Those things can be ARM processors, PowerPC, or any mix of others. RISC-V has become a very common contender, being open source and not having to pay a lot of royalties to develop chips. Renesas continues to be the king because they're like dirt cheap and a real pain in the butt, but we won't go there. So firmware holds the goodies. If you're doing reverse engineering of an ECU or an infotainment system or a telematics device, there's firmware in there. That's where vulnerabilities typically occur that are remotely exploitable. We'll talk about the remote proximity and local exploitation attack vectors shortly. So compiled code, you don't have a car that runs on Python or BASIC, where interactive BASIC or Perl. You have it in compiled code, typically written in C or C++ or some other compiled language for high power and speed. So we've continued to see over the last 6 or 7 years, automotive OEMs keep getting better and tier 1 suppliers keep getting better about security. They're wrapping in more techniques to secure the vehicles. They're going through, they're implementing processes that help create code that's better. They're engaging with security folk like myself to make sure that they're seeing what they're seeing. But they're also adding more complexity and more connectivity and more interactivity as we get into autonomous vehicles and electric vehicles. So we can't say that things are getting better. I'm not going to say that they're, oh my gosh, the world is ending. But please note, as they get better, the world is not necessarily getting better. So one of my favorite movies about car hacking is The Fate of the Furious. One of the Furious movies where a hacker takes over hundreds of vehicles and drives them out of parking garages and basically creates a mob in the street to create an end, We won't talk about that much, but let's think about what it really would take to do such a thing. We can argue all day long about whether it's possible, how hard it would be, how many, but let's talk about what it would take to do. Because you've got your transmission that's controlled by an ECU, you've got your engine that's controlled by an ECU, you have your brakes, your accelerator, your steering, all controlled by electronic control units. So the process starts out by discovering exploitable bugs. Not every bug is a security vulnerability unless a denial of service or a crash is enough to be considered a security bug. But exploitable bug, let's talk about a bug that can get you code execution on a computer system like your power steering control module. Discovering exploitable bugs, depending on the complexity, depending on how much learning has to go and how big the system itself is, discovering exploitable bugs can be measured in months at times, sometimes days. Every once in a while, a few hours in, you'll find a bug that's exploitable to gain code execution to do what you want as an attacker. Once you've discovered an exploitable bug, it takes potentially days to create an exploit that is tested, a true, rock solid, doesn't crash the thing, cleans up after itself. The thing that many people, and probably not you, but many people outside the industry don't understand is actual exploiting bugs, once they're discovered, can be done in seconds. So that's not the war that we're trying to fight. A lot of people I talk to are like, oh no, it just take too long to. No, actually, once they've done the work, it takes a matter of seconds to exploit and then pivot through other computer systems that you can then exploit with other vulnerabilities. So just a moment to talk about timing. So discovering exploitable bugs, this is where most of the work really happens. So in automotive, we're talking about an entry point. And then we have to carve a path of exploitable bugs, potentially, to get to the thing that we want. So entry point could be your infotainment system or your telematics device. Why do I say that? Because they're the ones that typically have a cellular connection and maybe available over the internet or over your cellular carrier or yada yada, or from other vehicles. So you don't have to be in close proximity to a vehicle to exploit those. So that's the remote vulnerability attack vector. While we're at it, let's talk about a proximity attack vector, like things that are line of sight, short range radio, Wi-Fi, Bluetooth, your TPMS sensor, your remote keyless entry, your passive key, all the radio devices that are on your car. Let's call that proximity. Nobody gets to see me touch the vehicle and I can exploit it. So I can do it from a house across the street or whatever. And then finally, the local attack vector. Now, local shouldn't be written off as, nobody can touch my car, because if you take your car in to get work done on it, your mechanic may be evil, or maybe they use tools that connect to the internet that get compromised, and that the tools become evil. So you can't write off a local attack vector out of hand. But those are your three attack vectors that you want to consider when attacking vehicles. So discovering exploitable bugs, this is the hard part. We have to dive deep into how a computer system works. So looks like we have a few people who've got some C experience and some other programming experience. Very good. So here's a C program, a very basic C program. It's the definition of the simplest. When you're learning to program in a language, you write "Hello World." It's your first program. It's basically just teaching you how the language works. This is that. So the main function calls to print out the string "Hello World" and then return exit success. The program worked. So we compiled that, and the main function on Intel x86, AMD 64, if you will, that's the 64-bit version, looks like this. It's a little bit more obscure. You've got to do more details. And finally, you end up manipulating the system over here And then we see call, put S. Oh, the compiler changed what it is that we call. That's fine, not a problem. So, but all this is to set up a call to a library function called putS, which is often used in place of printf if there's no format string that really gets used. Okay, so that's Intel. Look at it in PowerPC. Now, if you're familiar with Intel assembly and PowerPC assembly may be more difficult for you, trust me, most people it's difficult for. PowerPC is a real pain in the butt. So we set up the stack, or we have the prologue, function prologue. We set up the stack for our call, and then we branch with length. This is a call to put S, and then we clean up and exit like we should. So kind of mind-numbing for a 1 or 2 line function. So I'll admit, those are the worst case scenarios. Those were using objdump, a open source and very low level, hard to use tool set. So this is Binary Ninja. Binary Ninja printing out, okay, this is prettier. You know, the colors give us something. This will say, Binary Ninja says for, hey, this right here, that actually accesses this string called hello world. Hey, that's very nice, thank you. Or we can even go as far as to use Binary Ninja's decompiler, which decompilers make code easier to read, maybe easier to understand the idea of what's going on, but it's easy to miss things. Some of the details that would jump out at you in assembly, they get reduced to just a couple characters in a decompiled world. So use decompilers. Don't trust them to teach you what you need to know, because C lies. I would rather read assembly or disassembly code than I would read C code, with the exception of comments and function or variable names. So reverse engineers, we've got to make sense of all the machine code languages, not just what does this instruction do, but these instruction groupings, what do they really mean? What is the intention? We have to identify data structures, because if you've written code, you know data structures are where you store a conceptual object. In fact, object-oriented programming is largely just structures with some code attached to it. So we need to understand what the code's doing and be able to play with it, either in our mind, on paper, or writing tools to interact with it. Which can lead to this. There's so much learning that goes on. Every assessment I've done, and I've been doing this for 17 years, every time I reverse engineer something, I learn something new. I research things. I try to get better at things. And then I'm trying to take those instructions that make sense separately, but turn them into what is the flow actually doing? What is this function really doing? Et cetera, et cetera. Brief teaser. You'll see more of this at the end. This is a picture of my favorite reverse engineering tool called Vivisect. So let's talk about emulation. So emulation, as we discuss it, we're going to talk about an interface where it's very much like a debugger, where you're walking through code and you get to single step, and you can multiple step, you can inspect, you can modify what's in memory. I'm going to just throw it down and say emulation's better than debuggers. And the reason is not that debuggers suck, because debuggers are really powerful. Debuggers are relatively cumbersome, because in order to play with a certain set of code, you have to, oh, hey, put a breakpoint at the code, and then it stops, and then you get to play with it only if you can trigger the code to get to trigger the instruction pointer to get to the code that you want to play with. So you have to know how to get the code, the device to execute code that you want. Emulators are a lot more, or can be a lot more flexible. Most of you have a certain idea of emulators we'll talk about in a second. Emulators can be a lot more flexible and lightweight. So there's no requirement for real hardware. That's very helpful in a lot of cases. They are easier to program and load because your program can just be a string or a file on your hard drive. There's no OS to restrict you. Now, we'll talk about that in a minute. I feel like I missed a slide. Oh, we'll get there. So emulators can do snapshots. So you've got virtual memory, you've got your registers, and you can just say, okay, save that to disk. We're good. Now we'll come back to that. Oh, we can emulate from there now. Emulators, specifically partial emulation, which we'll talk about in a second. Partial emulation can allow you to discover what code does without having to set up an entire environment and run through all the initialization code and try to make sure that the instruction pointer somehow finds its way to the code that you want. And we'll talk about that in a few minutes. Malware can't infect your partial emulator, well, unless you work hard and want it to. I have had malware infect one of my emulators once, but that was a very special case. So it feels like a debugger, it smells like a debugger, except when you don't want it to. You can change how the emulator works a lot easier than you can change a real machine running real code with the debugger that gives you some injection points into that. So let's talk a little bit about reverse engineering and vulnerability research. So these are very highly personalized things. I've interviewed a number of my friends who just trying to get better and learn because I've got great respect for them. And their processes were all over the map. Now, there's a lot of overlap. We identify the same things that are important, but the process that we go through is distinctly different based on how we get to know unknown space. So there are two basic camps for vulnerability research, though. There's the dynamic camp who like to run fuzzers and running code in the environment that it's supposed to be, and typically with a debugger attached or something like that. Because if you're fuzzing, you cause a crash, you want the debugger attached so you can jump in and play with it. Or static analysis. Static analysis, people who take disassemblers and compilers and code analysis tools that run over code that's not executing on a computer system. So I've found that the best option tends to be a hybrid of both of these approaches. And I don't think that anybody anymore really falls into just one camp. But emulation allows a bridging of these that is pretty special. This is just because I wanted this to be in the slide deck. It has nothing to do with the flow of this talk. But if you have significant knowledge of UDS, and I can see that a few of you do, that's good. You might recognize the hex 27 service that this function is dealing with. That's the security access service. Okay, intro to emulation. Emulation really is a simple concept. Most of you probably have run an emulator of some sort, like the MAME emulator, or this is a CP/M emulator. That this was like my first introduction to emulation 20 some years ago. Those are emulators. They're great. They do a full system picture of what emulation really is. But at its core, emulation is creating a virtual CPU with virtual registers, virtual access to memory. And when I say this, I'm talking, I write a lot of my emulators in Python, where the registers really are just a variable on the processor class object. And the memory objects are pretty much strings. So it doesn't have to be, oh my gosh, the mystic arts. This is real accessible stuff. And then a bunch of instruction decoders. So you've got move instructions and store instructions and all the things that a given architecture has to do. You write some code that does the thing on your virtual memory and your virtual registers. And then you emulate through each instruction. So the real, like, if you really want to go hardcore and do a MAME emulator or CP/M or whatever, a lot of the things that take a lot of time and are kind of more tedious for vulnerability researchers like me is if you want to implement peripherals like a serial port or a CAN peripheral. But for many things, that's not necessary. For what we're doing in reverse engineering, it's not necessary. I am involved in a project to create an emulator for Cummins 2350 ECU for Cummins engines. It's part of a DARPA project, and there we're implementing a lot of peripherals, but it's seldom necessary for what we're talking about today. So let's talk about partial emulation. What the heck is partial emulation? If it's not my MAME emulator or QEMU, what is it? So partial emulation is the concept of doing the things that an emulator does on what you want, where you want, and when you want, with as little setup needs as possible. So for example, to facilitate this, we will talk about a few features of partial emulators, like Vivisect has partial emulators for almost, well, yeah, all the architectures that it officially supports, and the ones that are coming, they also come with emulators. We talk about safe mem. So if I've got an instruction that says, please read this from that memory location over there. Let's say that memory location doesn't work. What happens? In a debugging world, the debugger throws an exception and the program crashes, or allows you to change it or do something, or the program crashes. Safe mem says, I don't know what it is, but I'm going to give you just some canned response that's identifiable. I think for a lot of the emulators I do, it's lowercase b's for every byte that you read. So 62, 62, 62. If I write, it's the same thing. I write nowhere to write. The thing doesn't exist. Okay, move along. Let's just act like it worked. This is not a pure play emulator. Nothing is going to be absolutely accurate if you're not reading and writing from real locations, but you can keep going. And for analysis tools, this may be something that doesn't matter. We introduced the idea of taints into partial emulators. Taints are values that get stamped into memory or registers that they're just something that your system can look up and translate back into what it was. So, for example, when we start out a function emulator, we pre-dope all of the places, a bunch of potential arguments to the function with a taint value saying, hey, this is arg0, this is arg1, this is arg2, this is arg3. So that it's really a number, some large number, that when you take that number and you ask the system, what is this? The taint tracking system says, oh yeah, that was arg1, but it's offset by like 25. So you took arg1 and you added 25 to it. We also have the ability to log reads and writes. This is very, very powerful. I've identified inline mem copies using an analysis module that looped through whatever loops there were, and it looked for reads and writes that tracked along and did what a mem copy does. Path tracking. This is also very fruitful when you're emulating through something to have keep a log of what stuff you've hit. Darn it. Getting too excited here. So we also have we have the ability to cover all branches. So if you're going down, you remember in a function graph, you've got nodes that are connected, and there are branch nodes where there are conditional branches where decisions are being made. Oh, is register EAX equal to 0? If not, go this way. If so, go that way. What if we could say, doesn't matter? Let's just make sure that we emulate through all the branches so that we can get an idea of what each instruction, what the context for each instruction is. So that we can do with partial emulation. And then finally, we can substitute functionality. So if there's a really massive, ugly logging function that I really don't care to emulate through, but I know what arguments it takes, I know what it does, I can slap in some Python code that just does the thing. If there are calls to imports, if you're dealing with non-firmware related things, or if you're talking a full OS firmware, If you've got DLLs or shared objects libraries that you don't load in, you can hit a mem copy, a call to an external mem copy, where you can just hand in Python code and it says, oh no, I know what that is. You don't need that library over there. No biggie. So you can do imported libraries. You can also do system calls, like what happens when a user mode program calls a kernel mode functionality. You can say, oh yeah, cool, I got code that handles that. The idea being to create an ecosystem that doesn't require all the setup and state tracking, and I want to remove the magic from actually getting to the code that you care about. So partial emulation is really powerful for a bunch of things, but the core two that I focus on are analysis modules. So I write code that analyzes code and then spits out something that's important. Looking for inline mem copy, I already talked about. Function analysis, we'll show you in a second, or ROP gadgets. I've used this to find a particular ROP gadgets that I want. Interactive mode is what we're going to talk about at the end. It's the debugging type emulation, but with a partial emulator that allows you to be very forgiving. So we're all all we're really trying to do is answer questions, right? We want to walk through, we want to know what code does. We want to know context around what's going on. We want to understand what's in a given register at a given point in code. And so Vivisect actually does this without any additional thing, where if you right click on a place within a function, you can see on the upper left, this is a function graph. If you right click on that 24348 address, you go down to the function submenu and you click show emulator state, and a partial emulator will be strapped in, set up with a bunch of taint values for arguments and whatnot, and then a path found to that location in the function graph with an emulator dragged along with it. And on the lower right, you see, okay, we've got a stack delta of -160. Okay, that's good to know. Here's the instruction that's there. And here are the operands for that instruction. So R3 equals, and this is a taint value, and it says, here's the hex, here's the decimal, and here's what it actually translates to. So that's the original R3 register going into the function. And then this second one, R24 and R11, added together make this hex 40002001C hex, which equals 616161. Okay, it's lowercase a. So sorry, this one, it must be lowercase a for the safe read. Getting into analysis modules, this is actually this is the important code for an analysis module that I wrote and I use all the time. It's called func recon, or function recon. The idea is I set up an emulator and I point it at a function and I say, hey, make sure that I hit every instruction at everything that descends from this point that is easily identifiable. Some switch cases can be more tricky, but emulate through all that and return a lot of interesting things. As you can see, this is 20-30 lines of code that's not that hard. It takes a little bit of knowledge of the emulator and a little bit of knowledge of Vivisect's opcodes and stuff, but it's not hard. And here's the result. Here's the text version output. It just dumps it into a scrollable text window. And on the right-hand side is the more formalized GUIfied thing, where it goes through. Func recon grabs strings, for example. Here are all the strings that it ran into during this function emulation pass. Here are all the imports that it ran into. This was off of a raw firmware. There are no imports in raw firmware. And here are the functions that are named. So if it runs into a function that doesn't have a name, like sub underscore or whatever the default name is, it won't list in here. And then here are the immediate values that it ran into. And right here, given what I know about this processor, this is a RAM access. And here are the instructions, here are the addresses of the instructions that accessed it. So one of the hard things when I'm first starting out, I'm trying to learn what a new target does. I don't want to burn a lot of time, but it can just take a lot of time. I want to make sure that I'm saving that amount of time for the important stuff. So I start off with reconnaissance as I'm going through maybe a main function. I'm just like, hey, what does that do? What does this do? What does this do? Maybe 5 to 15 functions that I run this function recon, and I've got a pretty good idea where the major things are. Oh, by the way, during function recon, this thing ran into a serial number. So that was very fun. So let's take that one step further. So that was analysis modules, things that I've written, I can run on code. And then I wrap a partial emulator with a debugging interface, as you see on the side, on the right side. So here's an instruction. Here's the, well, start at the registers. Here's all the registers at this given state, and these are taint values, because that's what I did. And here's the instruction. After the instruction happened, here's what that looked like. By the way, it tries to take what's in R0 and LR here, and it says, okay, that's actually uninitialized register R0, and that's uninitialized register LR, because we're on like the first step of the emulation pass. Highlighting what changes, yada, yada, down here. What I've done here is I'm hitting enter on the right-hand side, and it's emulating one thing after the other, and it's just dragging me through, kind of taking me for a ride through the function graph on the left-hand side. You got multiple monitors. This gets really pretty and is very nice. You don't even have to look at the emulator until you decide to, but you can just be given a tour of the code that you're working on. And this is easier to read, the same things, but given that this is a digital presentation, you probably could make out what it said before. So in conclusion, emulation is a really untapped resource. We've only touched what emulation can do. This year, a guy I've been working with released a tool called Vivisection or Vivisect Ion at DEF CON, and talked about a lot of the same things that we talked about here. The idea is to bring context and capability to easily create custom analysis modules to help you understand what's going on in a processor, in firmware, in code at a very specific point, with side-by-side emulation walkthrough and fake OS, so that we can do great things and make the world better. So this is my contact information. Please reach out if you have any questions or comments. I appreciate your time. Thank you.
Thanks a lot, Matt. That was a super talk. Basically, I really enjoyed the talk, and I mean, I have a lot of questions for you as well, actually, on this. So essentially, like you talked about, like emulation, like these emulation approaches, like compared to dynamic analysis, like what advantages would, let's say, like in your opinion, like what advantages would dynamic analysis have, like over emulation approaches, and vice versa, basically?
So the dynamic analysis is going to be faster because you're operating on real hardware, and emulators are always running a layer of additional abstraction. That said, I believe that you can answer questions better and more programmatically in an emulator than you ever can with a debugger. And I've done a lot of programmatic debugging in my time. But you're always constrained by other people's rules. So I kind of think of an emulator much like I do the Matrix. You remember the first Matrix movie when Neo finally realized that, yeah, I'm dead, but forget that. That's not true. That's what you can do in an emulator. If he'd have died at the end, that would have been like dynamic analysis with a debugger, because he's really at the mercy of the system. Does that make sense?
Yeah, no, that does make sense. It's interesting you said that dynamic analysis might be a bit faster, because in my experience, I think like the overhead of essentially like spinning up your sandboxes and setting up that whole sandbox environment, even though it's automated, like that whole, like all of that could add a lot of overhead. And I thought like symbolic analysis would always be like the much faster approach, perhaps.
So this talk's focused on emulation. I've done a ton of symbolic analysis as well, and I love both. They are a powerful counterpart, but I needed to focus on the emulation just for this one. But symbolic analysis can be very fast. Wow. So yes and no. And here's the long and short. Symbolic analysis relies a lot on generating code paths to do symbolic analysis on. It takes a lot of resources, but the details that it can answer, the detailed answers you can get from symbolic analysis, and even to a lot of extent from emulation, allow you to answer fewer questions. So dynamic analysis, there's this vast space where fuzzing, for example, I mean, largely that's dynamic analysis. You have, you're trying to answer a problem or two, but you're just forcing all the stuff, trying to generate something that causes a problem, gets you to the code that you want to, and whatnot. Whereas with emulation, you can answer a lot of early questions that zeroes in on the thing you're really interested in, and symbolic analysis as well. Symbolic analysis can be actually a lot slower per instruction than emulation or debugging, because the processor is fast at executing instructions. The emulator actually does a lot of that as well, and doesn't track as much information. But symbolic analysis allows you to zero in very quickly on the thing that you're seeking.
And how far do you actually go with emulation? So you talked about, I mean, like your typical applications could be making system calls. You mentioned, like, let's say like DLL loads and all. So would you essentially be emulating like that part as well, or would you essentially at some point be making those real system calls and loading those libraries and then delegating to those libraries to sort of like run those actual functions behind the scenes?
So that's a great question. And it is not one that has a set answer. So one of the things that is on the docket for Vivisect is the ability to load a bunch of different libraries and an executable into the same workspace and link them all together. So while emulating, you can say, okay, I've got libc here, I've got the target binary here, and I jump to the import of memcopy, and that actually goes in and does memcopy. But Vivisection, which I'm using a lot, plugs in a lot of standard POSIX and Windows functions, and just has Python just already strapped in, just ready to go out the gate. So whether I use one or the other really depends on the context of the target binary.
Interesting. And basically, like when you're doing your typical like reverse engineering analysis, would you essentially, I mean, like between static, dynamic, and symbolic and emulation approaches, like what would like how do you basically like order those that sort of sequence for analysis?
Yeah, how indeed. Different problems lend themselves better to symbolic analysis or emulation or pure on debugging. Pure on debugging is going to be more trustworthy in certain circumstances about initialization code and whatnot. When I'm doing emulation, I'm typically not wanting to bother with all that. So oftentimes but I want a lot of play, which allows me, which I'm allowed in emulation. So sometimes I'll actually start up a program in its natural environment, attach with the vulnerability debugger, the VDB, and do what's called a V snapshot, and snapshot all of memory and processor state down to disk. I have tools that then translate that into a Vivisect workspace for static disassembly, because the analysis that goes into static disassembly is so much way better than anything that you'll ever find in a debugger. But it's already set up. All the initializations codes there. I can stop it at a given point, and then I can jump in with an emulator, and I can have the environment set up the way that I want it, and then emulate the things that are really interesting to me. Okay. And that also plays into symbolic analysis as well.
Sounds good. And but I think we have to wrap up because we are starting our closing session soon. But a great talk, Matt. Really enjoyed your talk. And thanks to the audience as well for your time. I'll end the session with this. Thanks all.
Thanks all.